So, MLS. Let's talk about a little bit on how Signal does the job on like having a conversation, an end-to-end encrypted conversation. So usually we have a ratchet tree of like a ratchet engine that will use the keys and etc. But I'm going to draw very simple things here and then talk about how MLS fix different issues or certain issues there. So if we have a one-on-one conversation and we want to talk in a secure way, uh, fast forward a lot of like different approaches that we can take here, but the Diffie-Hellman standard that we are using, kind of the exchanging the private and public keys, is the standard nowadays because it's the most secure one. And it's solving like on top of like TLS and etc. It can solve a lot of issues for us. And it actually, that makes like end-to-end encrypted messaging possible at all. So what does it mean? We have a private key here, we have a public key here, and for this one as well, we have a private key and we have a public key for like Alice and Bob. So they only need to exchange their public keys together and they can talk to each other. So what they do, usually when Alice wants to talk to when he wants to send a message to Bob, they usually use Bob public key and sign the message and they say hi and they sign it like with their public key. And then we'll send it to Bob, and Bob with his private key can decrypt it because when he receives it, he can read it. Otherwise, only needs the private key, and when decrypt the message, he will see the hi. So that's a one-on-one conversation. But what if we want to have a group conversation? So we have like many parties in the conversation. What would happen here with this structure? We need to exchange public keys and private, actually the public keys with all of the participants in the group. So if Alice is here, Bob, and etc., so they need to send their public key here, here, and the rest will do the same. And it would be a complete graph. It's a very huge and like expensive transferring data, because just establishing a conversation to have the conversation ready to go. And the another like cost-effective part is when I want to send, like Alice wants to send a message like a normal hi to the group, that everyone in the group. What would happen? He needs to like encrypt the message for every participant in the conversation and send it to all of them, and send it to those parties, and those will receive it and then can decrypt it. That's the kind of the normal flow. I would say nowadays WhatsApp, Signal, and others, they came with like some better solutions, but still in the background it's kind of the same thing. So you need to have like a lot of keys exchanged between all of the participants, and you end up with like a secure conversation. And that's one of the reasons actually that we end up with like we don't have large groups as Telegram and secure messaging systems, or like it takes so long for WhatsApp to have channels and etc. Or even like syncing between clients. But still, different reasons, different problems, and different solutions came along. But let's move on to MLS. So, as I mentioned here, when we have a group, we need to, like, every participant needs to send their public key to the other participants. And that would be very cost effective because they need like to exchange these keys. And if they want to like keep the security properties that we're going to talk about them, like for example, the forward secrecy and the post-compromise security. So what does this mean? It means like the forward secrecy means if like from now on, like if someone gets your keys at this very particular moment, they can decrypt the messages from before. So for example, if I say hi and I say howdy, so if they get the key here, they cannot decrypt the messages before. And for the post-compromise security, they can't decrypt the messages from the future as well. So if someone sent another message, hi back, because the key here was compromised, they should not be able to decrypt the upcoming messages as well. And that what requires, like what we need to do to achieve this, we need to rotate the keys by every message we exchange. So do you remember that I said here, every single like peers of the conversation needs to exchange their keys, the public keys to others. They need to rotate the keys again after each message and then send the messages like the keys to their like the other people there, and then they will use the new keys afterward. And that would be, it means like, for example, if I say hi to the group, I encrypt the message for everyone in the group, and then I need to send my public key to all of them again. That means that, yeah, that's my new public key. So from now on, for the next message, you need to like use that key. It's not that so simple. It's not like always the sending messages, because as I said, there are like a little bit more advanced solutions how to avoid not sending a lot of keys around, like limiting the time period, like using a ratchet machine, like they ratchet like the keys, they getting the keys from other keys, they exchange like some security keys beforehand, and etc. and etc. So they can solve like a lot of these issues, but still it's very expensive. So as you see here in this part, it's a graph. It's a graph, it's a complete graph, so it's very expensive. So we need to come up with another better solution that's specifically designed for groups. So before MLS, we didn't have like a very good protocol standard way to like create an end-to-end encrypted group that was designed from scratch for like end-to-end encrypted conversation and for groups, not one-on-ones. So what happened here in MLS, instead of like having a graph of users, we have a tree of users. Like each node here, each leaf here is actually a client, or we call it installations. So in this tree, all of the members will be on bottom of the tree, or yeah. So the leaves are the users that we are like we are the members of the group. And it's always like it's a binary, it's a complete binary tree. What does it mean? It means always it has like the leaf nodes complete, even if we don't have enough users to complete the tree. For example, if we have 3 users, what we will have will end up with this structure. So we have 3 users, Alice, Bob, and Charlie, and this node will be empty because we don't have someone to fill it out. But what would happen for that? It will be empty if we add another person or another client that will be filled. Otherwise, it will be empty forever. And it would happen like the same for if we remove like Bob from here, that node would be empty. If we restructure the tree, we can like reorganize the tree again, and it will be changed to a better structure. But yeah, that's the like we need always to have the like the balanced binary tree. It means it doesn't matter if you have empty nodes, you need to complete the tree fully balanced. So that's the structure of the group. But what does this mean? So we need to take a look on the properties, the security properties, how we exchange messages, where are the keys here, and how people like gets added and gets removed from the group, etc. So we talked about like how we are exchanging keys in like normal signal protocol now. If we have 2 people or 3 people, we exchange the keys for each member to other members. But in MLS, we have the tree. I'm gonna like draw a tree for only 2 members here. So here Alice and here Bob. So Alice and Bob will have a private key and public key again. But instead of like exchanging these keys, they will share kinda private key, not kinda, real private key with their parent. Here, their parent is the root. So the root also has a private key and a public key. So what would happen here? You can actually calculate, and actually this node will be aware of their parent private key. So this node Bob will be available of his parent or his ancestors' private keys. and Alice as well here too. But they cannot see the private keys of others. Why? Because a kind of a mechanism here, if I want to like put it in a simple word. So we use a mechanism to like generate the keys, but it's not backward compatible. So it works in one way. So for example, if you have a key here, you can come here down. You can't come here down and understand it, but the other way it kind of work. Here the same. So Alice knows about the root key here, the private key, but doesn't know like the root doesn't know about Alice's private key. So at the end, what would happen here if Alice wants to send a message like to Bob? So they only need. So let's me grow a little bit. Later I will like make a bigger tree here, but here I just want to send a simple message for Bob. So Alice, if wants to send a message, instead of like using Bob public key, they can use the keys from the root and send the message to the roots or the parents of those recipients, and that would be the responsible part of handing over the messages to these and other leaves. And in, because as I mentioned, they know already aware of the keys for this root, they can decrypt the message. Let me just make it a little bit bigger, and then we can maybe understand how that would be efficient here. So let's have a group with 4 users or 3 users. So here, if Alice and Bob and Charlie and Dave wants to exchange messages. So before I said, if Alice wants to say in Signal protocol, for example, if Alice wants to send a message, they need to send and decrypt the message for Bob and Charlie and Dave, for all of them, and send the message to everyone there. But in MLS, what they do, they only encrypt the message for this root here, for this one, and for this one, for example. Actually, they don't need to kind of sign it for here. So what they do, they only sign it twice, and that would happen. What would happen? Here, they can use the keys, and because of the structure that I said, they can kind of derive the keys and understand what was the key that the message was for it. So as I mentioned before, we always have a public key and a private key. So here has a public key again and a private key. Again, a public key and a private key. And here the same, PK and pub key. Pub key. Okay, so what would happen here? So if Alice wants to send a message to everyone in the group, instead of like getting the key from Bob, they only encrypt it for this node. And since everyone below this node can understand the keys from that node, they can decrypt the messages as well. So that would happen because, as I said here, they already know the information about the parent of their parent here. So here is the same. Bob knows the keys of his parent. And since we do it here again in this part for this key as well, this means they can do it here as well. And all of these people and participants will decrypt the message. So if you look at the group, now it has 4 people in it. It's not that big, like a bigger change, but if you like assume you have hundreds of people in the group. So let me draw this simple tree with 8 people. So in the normal Signal group, if I want to exchange a message here, I need to send a message for 7 people, but here I can send it to 3. And that would be the big performance change and shift here. So it would in the tree, it will decrypt all the messages and send the messages because they all share the key. They know about the keys. They can decrypt the messages without using a lot of keys here. So that's the first structure that we need to know, and the tree and the keys. So please, if you have any questions, go ahead and ask. I try to not go that deep because we have like different trees, different secrets, different things we want to do. But I'm gonna like do a high level overview here, and maybe like we can do it later or even today. Now, if you have a question, we can go a little bit deeper. So another thing here. So as I said, here all of the clients or the users laying down. Actually, we're not talking about users in MLS. We're only talking about a client. So for example, if Alice has two clients, 1 and 2, this could be 1 and this could be 2. And Bob have only like client number 3, it could be here. And Charlie have 4, 5, 6, it can be 4, 5, 6 here. So we're not talking about users, we're only talking about the clients or installations. So if we want to add or remove a user to this tree, what would happen? Because I mentioned we have the forward secrecy and the post-compromised security, sorry. So as I mentioned, all of these nodes has private and public keys. And everyone in the tree kind of has like a view of the tree and the secret tree and what are the keys. And we want to make sure that if we change the group, no one from before or from like the future can decrypt the messages based on the state they were aware. So let's assume like Bob wants to add a new client, they call it 7. And we put it here. Since the group changes, because this node was empty and now has a client in it and has keys in it. So here, here what we do, we change the whole keys of the structure of the tree. What we do, how we do it. So 7 will introduce a new set of keys, a private key and a public key. They force their parent to change their key. And since their parent changes their key, this parent needs to change their key. Also, this one changed their key. But as I mentioned before, we have like a mechanism to derive the keys from our parent. So here, when 7 will be added, it will require this parent to change their keys. And when they change their keys, it will require this one to change their keys. And since the key here has been changed, they will derive it here and here and here, and the rest of the tree kinda start changing and shifting the keys. And that's one of the reasons when all of the keys has been changed, no one when removed or added can access the messages from before or the future. Actually, they can access the message, but they cannot decrypt it. That's the main thing, because the whole key set has been changed. So this is the group structure, and every group structure has a version to it. Like we set a version to it, we know which state we are at, and we call it epoch. So let's say we add the client number 7 for Bob to this group, and the epoch or the version of the group is like number 5. We add a user to it, we change the whole structure of the group, we change the membership of the group, we change the clients in it, we change the keys. So we create a new epoch or a new version of the group. Later, I will call it like a commit, and we talk about that as well. So the epoch will be increased to number 6. So now the group changed. Now we are on epoch number 6. Everything has been changed. And everyone updated their group state. Why they need to update their group state? Because as I said, every node here changed their keys. So if you don't update your state to the group state, because of these two properties and because of the keys has been changed, So you cannot decrypt or encrypt a message in the group. And that's one of the most important reasons that you see a message that you says in the logs, like unable to decrypt. The unable to decrypt, either it means that you are in the future epoch or in the previous epoch, in the past. But how that happened? So it means if you are in the future epoch, it means someone changed the group, either you or someone else, and you updated the group state. Let's make a timeline here. And this is epoch number 5, and this is epoch number 4, and this is epoch number 6. And here we add Alice, we add Bob, and we here remove like Dave. So let's say you are here. So you're here, you receive a message on that state, and you can decrypt it and you can see it. But like someone removes Bob, or Dave removes David from the group, and the group state is here. So, and that someone, let's name him like Alice with big A. So another client of yourself removes Dave, and the group has shifted to the epoch 6. And the other client of yours is still on epoch 5. And if Alice say, hi, I just removed Dave, you can't decrypt the message because you are on the wrong epoch. You're in the past. Actually, you can. Why? Because we allow in MLS, we allow to reserve how many epochs in the past you can still decrypt. For us in XMTP, it's set to 3. What does it mean? It means if you are still in an epoch from last 3 epochs, you will still be able to decrypt a message. But let's say if the epoch now 6 and you are epoch like number 2, you get an error. Certainly you get an error because the history of the group has been lost for you. Or if you are too far in the future, that you change the group a lot for yourself, but like other people that they talking to you, they are still in the like in epochs in the past or the other way. So that's the reason that you see a message could not be decrypted, because your keys and the group state that you have, it doesn't match. You don't have the proper keys to decrypt that message. That's one of the most important things that we encounter usually in MLS. The groups gets out of syncs, and that's the problem we always try to like reduce or like to solve and or to avoid. Actually the forked issue was something like that. If you wanted, I can talk about that as well. So but we're talking about messages. We're talking about sending and changing the group, sending a message, etc., etc. In MLS, when someone create a group, they actually init the group. And that group can be locally, nowhere else. It can lives on their client, on their device, and does nothing. They can do it. You can do it. Anyone. But if we want to sync on the server, we send all the information. Okay, we send to the server, yeah, we have messages for that specific group. We call it group ID, or we call it topic ID here in XMTP. So we have a group. We want to add a person to that group. We want to add Alice to the group. When we want to invite someone and that person is not in the group at all, so how they can get all of these information about the group? The tree of the group, the keys that I mentioned, who is in the group, what's the property of the group, what's the keys, what's the epoch, and etc., etc. Here, we shape or we create a welcome message. We create a welcome message for someone. We send it to the network. Actually, we call it DS, or distributed like system, distribution server. So the DS receives the message and tells the other to Alice, hey, you have a new welcome message. And when they open the envelope of the message, the welcome message, they see, okay, that's a welcome message. I've been invited to join a group, and I see the properties of the group, I see the members, I see everything. I decide to join or not. That's where you see the requested, like the requested part, that if you want to join to the group or not. So we get the welcome message, we create the group. Actually, let me do it here. Alice create the group from the welcome message. So Alice will shape the group on their local device the same as others have the group. Why? Because they want to exchange messages to that group. So Alice will be added to the group because they joined the group. But that's not enough. Why that's not enough? We only invited Alice to the group, but the rest of the team, the rest of the group users needs to like accept the change and put it in their tree, to evolve the epoch. The welcome only used to invite Alice, but what about the other members in the group? We use commits. A commit is not a normal message. It's actually it contains proposals. What is a proposal? Proposal, it's a proposal that we need to change the group, and the proposals has like different types. For example, adding a member, removing a member, etc., etc. So we send a proposal to others. Yeah, we want to add that person, and they can accept or reject it. There are like different strategies that we implement around the proposals. But let's say I want to add Alice to the group. I create the welcome for that. I send the proposals and the comments to everyone. And so I'm Bob here. This is Alice. And this is Dave. So I send a welcome to Alice. And then we have the commits that for others. Dave needs also to accept the commit to accept the commit. Why? To change their epoch from their current one to the one that Alice also added. So this flow can be different from implementation to implementation. I'm not sure which way we go around. Maybe you can correct me here. Sometimes we send the welcome, then the person who wants to get added send the commit. Sometimes we send them both at the same time. It's a little bit different. I'm not sure. I don't recall, if I look at that part of the code, how we treat this. So sometimes it's like we say, okay, Alice, if you want to accept our welcome message and you want to join, then you yourself send a commit that, yeah, I'm going to add myself to this group. How I can add myself to the group? Because I have access to the group state. So that's that's the way that we can like work on and we implement our way into like the protocol. So here, we have the commit, and we accept the commit, and we put the changes into the state of the group. For example, where we use the commits as well, if we want to change the group name, for example, here at XMTP, the group name, a group pin messages we want to add, for example, the disappearing messages we added. And everything that we want everyone to agree on and everyone be the same state, we put them in the group state, in group extensions, actually, the correct name. But we send them via commits and everyone needs to agree on them, and they need to keep the group state for everyone at the same level so they can communicate with the same group states. So this is a little bit about how things working. Let me just mention how we remove people. So for example, if Dave now wants to remove Bob, Again, they shape a commit with a proposal that we want to remove Bob from the group. So they send the commit over. And if at least one person, not about the remove, also the add as well, if one person or one client accept that commit, it means, yeah, okay, so now everyone needs to accept it and like go around that commit. So Dave sends the commits that we want to remove Bob. Alice accepts it. And then because it's accepted and Bob get it, because Bob sees, okay, I got removed from the group, they need also to accept it, and they remove the group from the client and like get out from like that state. But they can't like can decide to not do that. They can keep the keys and everything. But because whenever we add a member or we remove a member, we change all the keys, so they cannot decrypt the new messages. They cannot see the messages related to that group or even the commits or everything, because they don't have the keys to decrypt it. So they can be removed. And actually, that's the reason that we can't have like self-removal right now. Why? Because you cannot remove yourself. But how does that work? If someone can suggest that let's remove that person, why I cannot remove myself? Because when you create a commit, you also create the how tree, the tree we just mentioned here, this tree, this and all of the keys here, how the tree gonna change. So if you want to remove yourself, you cannot, it's not possible that you know about the tree, how it's gonna change. Because if you're gonna know how the group gonna be in the future, so you still can read the messages from the future. So that's the reason that we can't allow the user to remove themselves, because it's not possible. Because if you want to remove the tree, if you remove yourself from the tree, it means you need to know how the tree should be evolved. And that's collide, like it's a conflict here. It's not possible. So how does it work if you want to remove yourself? Like, for example, you can suggest to others, yeah, guys, please remove me. And they will submit a commit that means that let's remove Bob. And that takes time, because if like no one's online, what would happen here? And that's the problem we have with the self-removal right now. There are like different solutions, hacks and tricks and like solutions inside MLS protocol, but we don't follow, we don't need for different reasons. But I mean, that's one of the challenges that it's here, and probably you hear about it, why it's complicated, why we cannot like delete or like left a group. I would like to talk about one other thing here. So each client here has a like in their client, as I said, the public key, the private key, etc. So they have like many other moving parts. Like one of them, we call them credentials. The credentials are like some like security properties and structure that they can sign all of their properties and all of the information about themselves and like send it to everyone. It's not only about like encrypting and decrypting the messages. It's like a stamp and signature on every message that you say. That you send a message and you put your signature on it. It's decrypted, but the signature can be different. So we have the credentials, but what I'm talking about the credentials here, because we're using the identities here. So the credential, you can have a credential here, and you can put, it's like a different signature on top of the security properties of MLS that you have, that you can say, yeah, that's also my verification about, okay, I'm the real Mojtaba, or I'm the real one that owns that specific wallet. So how it's possible? Like, for example, you can be in this group, you can send and receive messages. Your messages are safe. Your messages are encrypted in the proper MLS way, but you can claim to be someone else. But how I can like verify your claim here? with your identities. And the identity part is where we can verify someone in MLS with their claims. Like, as I mentioned, for us in XMTP, that can be your wallet address. It's not your simple wallet address. I mean, it's not correct, actually. It's not wallet address. It's your like valid private key, public keys, your credentials from your wallet, actually, not the address. Let me fix it. So, and you can have different identities. Like, that's the reason that we can have infinite like identities. You can have a list of identities here, and it shows, okay, this person can owns actually, not can, owns these different identities, and they are really, who are they claiming? And that's the reason that identities is very important for us, and we're using them. And what else important for us to say? Yeah, so just again, the epochs are the versions of the group. That's very important, that we need to be in sync for every group. Oh, okay. One last thing I want to talk about is the key packages. So what is a key package? So do you remember here when Alice wants to add, sorry, Charlie or Bob wants to add Alice, and they want to put them in the group with us, but they don't know Alice at all. They don't know Alice, what they're doing, and etc., etc. So, sorry, 1 second. Do you hear me at all?
Yeah, I can hear you.
Okay, okay, okay. I just wanted to make
I
sure.
think,
Sorry.
yeah, I think people just had to drop because we're a little over, but I
Oh,
think you
okay.
should wrap it up whenever you're ready.
I didn't know that we're over. Okay,
It's
perfect.
okay.
Okay, so just gonna someone should have hinted me, like send me something, like I thought we have 1 hour. Okay, it's 30 minutes now. I know. Okay. So the last part about the key package. So we have the key package. We need, if we want to add Alice to the conversation, we need some basic information about Alice. Who is Alice? What their credentials? What their security properties they have? What they own? So that's the reason whenever Alice register on the network, they upload a key package to the system, and within this key package, they have all the security information that anyone needs to use for them to add them to a group. So we upload the key package to the network, and whenever someone wants to add us to a group, they use that key package and they shape the welcome message with that key package. And that's the reason that welcome message only tied to Alice client, not everyone else. And in the key package, we have the identity, we have everything else related to that client. And one last note is each client, again, not user, client, or installation, must have their key package separately uploaded to their network. That's the end of it. I wasn't sure at all if we're over, and sorry about that. But yeah, if you have any questions, go ahead.
Just a quick one. Are adds and removes the only kind of commits that have the potential to cause forks?
Sorry, could you come again? I hear you a little bit breaking.
It's in the comments. Are
Okay.
adds and removes the only kinds of commits that have the potential to cause forks?
Your last word, I don't get it. I
I
get
can
the.
say it. He's asking, are the adds and removes the only kinds of commits that have the potential to cause forked groups?
Oh, no. Actually, it should be like that. It should be, because updating the extensions, it's not changing a lot. So I'm not sure if we are actually, because it's the commit, it's a commit. So actually, no, it's any commit can cause the forked groups. For example, we had even changing the names in parallel could cause the forked group. So if I want to say it like, if you, okay, I'm not sure, like, do you hear me okay now? Okay, perfect. So the thing here, the group state, as I mentioned, it's always needs to be in sync, okay? But if we access or like change the group in parallel, that could cause the fork issue. It doesn't matter if you change the extensions or change the keys or change the epoch. Actually, the keys could survive. Why? Because we're deriving the keys. So we don't need like to be in real sync. We can easily derive the keys or even the epochs because we always can like go back to at least 3 epochs for now for our implementation. So you can survive from these stuff, but changing the group in async is a like very tricky and risky in MLS. So that's the big problem, and always like most of people are implementing MLS, they usually like hit that issue when they are calling the MLS group in async.